was the helicity of the single particle state, which had the interpretation as the two-dimensional spin in the CFT as the two-dimensional spin from the CFT perspective. And then what we did was to actually see what basically the inner product of these states are. And then we sort of convinced ourselves that these inner products are actually delta function normalizable when the scaling dimensions lie on what is known as the principal continuous series representation of the Lorentz group, where these deltas take values which are of the form 1 plus I lambda, with lambda being a real number. Okay. So finally the form of the 2-point function. So finally the form of the inner product, or equivalently the 2-point function between these two operators from these conformal operators on the celestial sphere had in that case had the following form. So now what we want to do is that we want to check explicitly that these states that we define, these single particle states, they do transform under the action of the Lorentz group, or equivalently the global SL2C as conformal primaries. Okay, so that's what we want to check. So okay, so let's go through that exercise in some detail, because this is one of the only detailed calculations that in this set of talks I'm going to bore you with. Okay, okay, so to begin, what what I will do is that we can write this single particle states, which is HH bar, ZZ bar, as follows. Okay, where this UR of ZZ bar is basically some unitary operator which acts on states in the Hilbert space, and this R of ZZ bar is basically a rotation operator which rotates some reference null vector, which let's say points in, say, suppose the Z direction. And what it does is that when it acts on a vector of this form, then it basically rotates this null vector to actually some generic form of the null vector, so in this case basically this is the parametrization. So in this case this is the parametrization which we have been using for a general null momentum. And so this basically this rotation vector takes you from this reference or standard null vector to actually this generic vector. Okay, good. So now what will for us it will be convenient to introduce some nomenclature. So basically what I will okay, so let me consider the set of all reference null vectors which are given by this. So you consider the set of all null vectors which are of this form and this set and this set of null vector and the set of all such null vectors, I will refer to this as the reference null direction. Okay, so right. So then what we want to check is that how these states, these HH bar, ZZ bars, they transform when you act with a unitary operator which implements some Lorentz transformation. Okay, so U of lambda is basically the unitary operator which implements a Lorentz transformation lambda when acting on the single particle states. Okay, so now as we just said, we can write the HH bar ZZ bar states as some rotation operator acting on some reference state which is of this form. Okay, so in this case the second line is just follows from our definition, and then what we have is the following. So now what I can, okay, so now in the third line I am doing basically some gymnastics where what we are doing is that basically so in this case basically what I have done is that basically I have resolved the identity in the sense that I have put in a factor of r lambda z bar and r inverse, and then this lambda of r was there from the previous line. And what this notation lambda of z means is that basically it takes these coordinates z and z bar, and it implements and it basically implements the following transformation on the z bar variables. So for example, lambda of z basically means az, it takes z to az plus p by cz plus t, and correspondingly for the complex conjugate. Okay. So now basically this object, okay, so now we have decomposed our unitary operator, which was u lambda, as follows. So we have this overall factor of u of r lambda z bar, and then we have this guy. Okay. So now right. So okay. So now I'm going to denote actually basically this operator. Okay. So now basically this object also implements some Lorentz transformation, and I'm going to basically give it a name, and we are going to call that let's suppose w lambda z bar of r inverse lambda r. Okay. So now basically what is this object? So this object basically belongs to the subgroup of the Lorentz group, which keeps the reference null direction invariant. Okay. And therefore that immediately suggests that so then this immediately suggests that this w should have something to do with the little group for massless particles. But in this case, notice that there is a crucial difference, because usually when we talk about the little group, we talk about the little group for a given null momentum. But in this case, I am considering the set of all reference null momentals. Okay. So therefore, from that point of view, it is natural to call this, it is natural to refer to this as a little group of the null momentum direction. Okay. So that's that. Right. So now what we can do is that it is actually very simple to compute what this little group actually matrix is. And that is very easy to compute, in particular in this SL2C representation, where in this case the various Lorentz transformations are just represented by 2x2 matrices. Okay. So basically, so this is some details which you can work out very easily, but just let me point out the essential steps. So basically, first of all, what we have to do is that we have to compute this rotation matrix, which takes a standard null vector to some generic null vector, and that is basically some rotation matrix, and that rotation matrix can be actually computed very explicitly, and in the SL2C representation, basically takes some form like this. Okay. Then you can obviously compute its inverse. And in this case, what we need is the inverse of r inverse of lambda z bar, where as I just said before, that lambda z is basically a shorthand for az plus p and cz plus t, and equivalently for the complex conjugate. Okay. So then you have these two matrices, R inverse and R, and then in order to compute this little group element, all you need to do is that basically you have to actually multiply these three matrices together. Okay. So you basically multiply R inverse, then you multiply lambda, which is basically this SL2C matrix, and then you multiply that with R of ZZ. Okay. So now I'm not going to show you all the details of this, but what you can convince yourself of is that basically after you multiply all these matrices together, then you can always put it in the following form. Okay. So the point is that you can always write the product of these three matrices in the following form. Okay. Where I have some diagonal matrix which is represented by this guy, and then some other matrix which takes this form. Okay. And in this case, this e to the power alpha is basically some particular thing. Okay, sorry, I forgot to write what beta was. So in this case, beta is basically some complicated object which we don't yeah, so which we will not need actually for the rest. Yeah, so for the rest of what I'm going to say. But the essential point is that this little group matrix, or basically this matrix which belongs to the little group of the null momentum directions can always be decomposed in this form. Okay. So now from that, okay. So now once we have this decomposition, it is very easy to actually sort of appreciate why I have written it in this form, and that is because of the following. So basically, this first matrix, which in this case was this diagonal matrix, which had this form, e to the power alpha by 2, 0, and e to the power minus alpha by 2. In the SL2C representation, okay. So this matrix So this matrix simply generates actually scale transformations. Okay. So for example, when this SL2C matrix, when this matrix acts on, let's say, the ZZ bar coordinates, it simply so it simply sort of rescales the ZZ bar coordinates by factors of the following form. Okay. Okay, so this is something very standard. So D of alpha, so the point is that D of alpha basically generates 2D dilatations or basically scale transformations. And what you can show that this other matrix, which we had in the decomposition of the little group element, which takes this form, so that basically generates 2D special conformal transformations. Okay, because what you can check is that when you act with this matrix on, let's say, the ZZ bar coordinates, then that basically gives you two-dimensional special conformal transformations. Okay. So okay, so with that, okay, so now what we have succeeded in doing is that we have succeeded in computing what this little group element is. But what we wanted to see actually was the action of this on single particle states in the Hilbert space. So therefore, we need to actually compute the corresponding unitary operator, which will implement the action of this symmetry generator on the Hilbert's on the Hilbert space. Okay. So then the corresponding unitary operators are obviously given by something like this. Now this form should be immediately obvious because we just argued that this D of alpha, so that basically generates actually scale transformations, which are basically generated by L0 plus L0 bar. This is something which I guess you are familiar with from 2D CFTs. And this other unitary operator U of S of beta, so that is basically generated by the generator of special conformal transformations, which includes L1 and L1 bar. Okay, and you can check that these matrices are actually unitary. For that, you have to use this slightly non-standard hermiticity condition, which is used here. Okay. So okay, so now let's see what the action of this unitary operators is on these single particle states. So for that, recall that this generator L0, so that can be written in terms of the Lorentz generators as follows. So this is something which we discussed actually last time. So for example, J3. So J3 is basically the rotation generator about the third axis, and basically K3 is the boost generator along the third axis. Okay. Hey guys, sorry, just give me 1 second. Lights have to be turned on. Okay. This has this weird thing about lights going off. 7. Sorry. Yeah. So so as I was saying, this J3 is basically the rotation generator along the third axis, and K3 is the boost generator along the third axis. Right, and similarly you can also write down, and similarly one can write down L1 as well in terms of L1 as well in terms of this rotation and boost generators. So now the thing that which I want to point out is that basically this L1 which is the generator of special conformal transformations, that can be written as a linear combination of actually these two generators, okay, B and A, where B and A are basically defined as follows. Okay. Now, if you have studied the standard sort of Wigner analysis of the little group for massless particles, then you know that this A and B are basically elements of the little group of the standard null momentum. And what one usually does in the standard sort of actually Wigner analysis is that basically you set the action of these operators A and B to actually 0 when they're acting on the standard sort of null vector. Okay. And these conditions are actually important. So it turns out that you need to impose these conditions in order to ensure that massless particles have a finite number of polarization states. Okay. So for example, if you have not seen this before, then I'd suggest that you look up Weinberg. So for example, if you see Weinberg's book, volume 1, chapter 2, then he has a very nice discussion of it. Okay. Okay, good. So then what we see is that basically since, okay. So then what we basically see is that this L1, which was the generator of special conformal transformations, that is related to these generators B and A, which basically annihilate single particle states. And that sort of from the two-dimensional perspective also has a nice interpretation, because that is basically the condition for being a primary, right? Because the way we usually define a primary is that we say that an operator is annihilated by the generator of special conformal transformations, right? And so this is how actually that emerges from the point of view of the Lorentz group. Okay, good. So then, okay, so right. So then, what we immediately have is that if I act with this unitary operator, which was where recall that this unitary operator had the following form. It was L1 plus beta prime L1 bar. So since L1 and L1 bar individually annihilate this state, then of course when this unitary operator acts on this single particle state, then it basically gives back the same state with eigenvalue 1, right? So then it is of so now we are almost done. So then what we need to do, okay, so now what we have is the following, is that therefore the action of the unitary operator, which implements the little group transformation, so that is basically given by this object now, right? So because what we just showed is that the action of the special conformal transformations is basically just trivial, right? So then so now what we need to do is that we need to compute what the action of this U of d alpha is on the single particle states, and that is also very easy to do. So let me just show you how this how you can evaluate the action of this e to the power alpha L naught. Okay, so basically we start with and actually the defining property of the single particle states. We use the fact that L0 is basically this linear combination of the boost and the rotation generators, and then we basically observe that when this e to the power alpha j3 by 2 acts on this state, then it basically gives us back the same state with an e to the power alpha sigma by 2, where sigma is the helicity, and that just tells us that this state is basically some state of definite helicity, and therefore it is an eigenstate of this operator e to the power alpha j3 by 2. But when you act with the boosts, then we know that but now the point is that if you act with boosts, then you don't get back the same state, of course, because energy momentum eigenstates are not actually boost eigenstates, and so therefore you get back a different state, right? But now since we are anyway integrating over all the energies, what you can do is that you can basically actually change variables, and then you can define so basically you can define a new omega by doing some rescaling of variables. And then you can bring this back to sort of the same form. But if you do that, then you basically get a Jacobian from this transformation, and that Jacobian combines with this exponential factor, and that Jacobian combines with this exponential factor, and it basically at the end of the day basically gives you this guy. Okay, and what I showed a couple of sort of pages ago is that this e to the power alpha is basically given by cz plus d to the power minus 1. So basically this is given by cz plus d to the power minus 2. And then we use the definition that h is given by delta plus sigma by 2. Okay, and so at the end of the day, what you basically get is this guy. Okay, so this was the action of e to the power alpha L naught. But then you can follow exactly the same steps and find out what is the action of e to the power alpha star L naught bar, which is just the complex conjugate. And then it is not a surprise that you get an answer which looks like this, right? So then, so then you combine these two results, and you finally get this guy. So basically, finally, we see that the action of the action of the Lorentz transformations on this conformal on this single particle states, on this Mellin transformed single particle states, is basically the following. Okay, right. And you also have this unitary rotation operator acting on the standard state, which was defined at z equal to 0 and z bar equal to 0. But but what this rotation operator now does is that it basically rotates you back to some generic point z bar. Okay, so then finally you can write down the action of the Lorentz transformation acting on this Mellin transformed states as follows. Good. Okay, and so this is basically the property that which I claimed last time was true. Is that basically this single particle states or this Mellin transformed single particle states, they transform so they transform as conformal primaries into the CFT. And if you sort of open any book on two-dimensional conformal field theory, then you will find that this transformation property is precise so this transformation property is actually precisely how actually quasi-primaries in two-dimensional conformal field theory basically transform under the action of the global conformal group.
Quick question. So in the derivation that you just showed, I thought Z was 0 when you showed that the state transforms with CZ plus D. Is it true for arbitrary?
So, sorry. So let me get back.
Here, even there.
Sorry.
So throughout the states are all at Z equal to 0. So here, when you have the CZ plus D to the minus 2H, so what is Z there?
So no, so in this case you are asking what is Z here?
Yeah, the prefactor,
Yeah, so in this case the prefactor here is some generic prefactor. So basically in this case we got this and actually this Z dependence, because you notice that what we were trying to compute is that basically we were trying to compute this object. Okay, so so we were trying to compute what the action of this little group element was. And that little group element actually is a function of actually some generic ZZ bar points. But what you were trying to compute is that how it acts on some reference state, but that reference state is defined at Z equal to 0, Z bar equal to 0.
I see. Okay.
Good. Okay, good. So are there any questions about this, guys? Okay, good. So if not, so then let us proceed. So okay, right. So okay, so as of yet, what I have been telling you about is basically how is basically the single particle states. But now a mode used for doing calculations and generically also in quantum, the way we do quantum field theory, is that it is useful to talk in terms of creation annihilation operators, right? Right. Yeah. So basically, in this case,
Maybe
yes,
I
Shubham,
can
go
ask.
ahead. Yeah.
Yeah.
Yes.
So what I was asking is the following: is that so last lecture you told
Yeah.
us about the 2 point function behaving in a
Hmm.
very weird manner. It's just some delta function, right? I mean,
Yeah.
yeah. So
Yes.
I was just a bit confused about like how the commutation relation with the, say, the dilatation operator
Hmm.
uh, like works out. Like I'm sure like this has been
Uh,
worked out, like in the sense that, for
so,
example,
mhm.
we know that like the
Yeah.
this action of dilatation operator on the 2 point function will
Yes.
be zero, right?
The
In
action of the
dilatation
yes. Yeah.
operator, because
Yeah.
like you
Yeah.
can take your d operator, the
Yeah.
differential
Yes. Yes.
operator,
Yes.
and
Yes.
this will
Yes. Yes.
now the in the differential operator, differential form of the dilatation operator is
Right.
just
Right.
x dot del x plus delta
Mhm.
I, and sum
Mhm.
over
Mhm.
the this
Right.
thing is equal to zero. Acting on the 2 point function
Mhm.
is zero.
Mhm. Mhm.
Now
Mhm.
how do I see this happening? Like, I mean, is there a clear,
Yeah. So,
because this is a delta
mhm.
function now, so like I was
No.
just
So,
wondering like
yeah.
how
So, no. So that is actually fine. So, for example, what you can explicitly check is that
uh-huh.
basically the 2 point function which we wrote down last time,
Yes.
that 2 point function transforms precisely in the same way as 2 point functions do in standard conformal field theory. Uh, and so from that it is yes. So from that, by construction, it will be annihilated by the dilatation generator. If we
Yeah,
active the
that is the thing that I'm a bit worried about, because like it
Mhm.
seems like, I mean, the
Mhm.
dilatation, this differential form of the
Yeah.
dilatation
So
oper
yeah.
sorry.
So actually, just 1 second, guys. I have
Yeah.
to switch on the lights again.
uh,
Sorry. Just I will just come back in a second.
yeah.
We got kicked out for some internet thing. Can you repeat the first question, Shubham, what you had asked?
No, I was just asking the, I was a very dumb question. It's basically that since the dilatation operator doesn't, so d acting on the vacuum state is zero.
Yeah.
Mm-hmm.
So
Yes.
like you can just then switch
Mhm.
the sandwich, the commutation relation between your dilatation operator and
Mhm. Mhm.
O1, O2, say, all
Mm-hmm.
Mhm.
right, in between two vacuum states, and eventually you will find out by some manipulations that the d operator acting on 2 point
Mhm.
functions must be
Mhm.
zero. Now
I
this
see.
2 point function, two point function, essentially, like from the last lecture we saw, it was a delta function.
Right.
Now
Mhm.
now I was just thinking that algebraically how does this work out, because this dilatation operator now is
Mhm.
some differential operator acting on a delta function.
Right. Okay.
And
Okay.
Mhm.
like the main reason I was confused is the following, that
No. So
yes,
that
last
yeah.
uh,
So yeah. Yeah. So yeah. So basically, in this case, yeah. So no, that I think has to work out actually. Yeah. So well, I might have to check
right, I'd be
I
very
might have to do the
happy if
calculation
this,
explicitly.
right,
But yeah. But I
because
think it has to work out because
yeah,
yeah. I
most
mean,
of the,
by
like why I was saying is that like
Mhm.
the most like I maybe not in 2D, but the way you said it,
Mhm.
it was
Mhm.
a valid prescription for like d
Mhm.
plus d and d minus two dimensional CFT, d dimensional flat space
Mhm.
scattering and d minus two dimensional CFT, right? I mean,
Mhm. Mhm.
uh,
Mhm.
now now
Mhm.
I am not sure about 2D, but
Mhm.
in higher dimensional CFT, like
Mhm.
it seemed
Mhm.
like, I mean, as the books that I read or I was
Yeah.
consulting, that
Mhm.
like
Mhm.
this
Mhm.
power law behavior is the
Yeah.
only consistent thing with the differential operator, like
Mhm.
the
Mhm.
identities.
Mhm.
So that's
Mhm.
why I was a bit confused about delta function, that like how does it
No,
must
so
work
that
out as you said,
mhm.
but like I was just thinking like
Mhm.
algebraically how does it work out, like do I have to
Uh,
use
yeah.
some
So
Yeah.
No, so no, so I don't think you will have to use anything fancy here.
Okay.
So yeah, so okay, so in this case, let me try to actually get back to you because
Yeah.
I
Okay.
have not
Okay.
actually done this
Okay.
explicit calculation myself. But yeah, but it should work out. Yeah,
Right.
because
I
the
I
point
was
is that
thinking
the
maybe
way we
you.
defined it.
Yeah.
Yeah, 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 yes. I
Yeah.
understand your point. Yeah, I understand your point. Mhm.
Okay.
Right.
That's all I just wanted to ask.
Okay, good, good, good. Okay, good. So, okay, are there any other questions? Okay, so yeah, so if not, let's proceed. Right. So, okay. So as I was saying, is that up till now we have been talking in terms of single particle states, but we can equivalently talk of, and what is more useful to talk in terms of creation and annihilation operators. So then basically from the definition of the single particle states, it is obvious you can immediately guess what the definition for this for the for the Mellin transform of the creation annihilation operators will be, and that takes a similar form which is given here, where this A is basically the Fock space creation annihilation operator for the asymptotic states in the S matrix. This epsilon is basically some convenient sort of label which takes values plus and minus 1 depending on whether the particle is incoming or outgoing in this matrix. Okay. So now from the yeah, so from now okay, so now what you can explicitly check is that okay, so now you can use the previous you can extend the previous proof which we did for the conformal transformation properties of the single particle states. You can extend that to the case and see how this creation and annihilation operators they transform under the action of SL2C. So in that case, you just have to, yeah, so the formulas become a bit more complicated because you have to write the unitary operator twice at every step. But the argument is essentially the same. And then it is no surprise that this operators OHH bar they precisely transform as actually conformal primaries in a 2D CFT. Okay, good. Okay, so now let me actually talk about, okay, so now having talked about the creation annihilation operators, sometimes it is also useful to talk in terms of wave functions. And this is, and actually if you read the original sort of papers by Pastarsky, Schominger and Shaw, they sort of, they actually talk in terms of wave functions rather than actually the creation annihilation operators, but that's an equivalent thing. So these conformal primary wave functions are nothing but just the Mellin transform of the standard plane waves. So for example, if you have some scalar particle, then in that case you yeah, so then in that case you can define these so-called conformal primary wave functions as basically the Mellin transform of your standard plane waves. Okay, and if you, and this Mellin integral can be explicitly done, and it takes some form, like this, where you have to where you notice that there is a divergence here. So for example, there is this q dot x factor, but that can diverge when this q dot x goes to 0. So you have to use some I epsilon prescription, and this I delta, and sorry, yeah, and in this case this I delta basically gives you that I epsilon prescription.
What is Q?
What is Q? Yeah, so in this case Q is basically the null momentum. Okay, so okay, so yeah, so in this case Q, okay, so Q is
No, I
basically
meant like on the left hand side there is no Q. So
on
Q
the
is
left hand
related to
side.
Z and Z bar, I
Oh
suppose.
yes, yes, yeah,
Okay,
yeah. So
sorry.
Q is related to Z and Z bar. So Q is basically this parametrization which we have been using.
Okay. That old. Okay.
Z bar.
Thanks a lot. Yes.
Yeah, 1 minus Z and 1 minus Z bar. Right. And yeah, so so whenever I write actually null momentous, I will write null momentous as p mu time equal to omega times some q mu,
Okay.
where q mu will be this standard. Okay, right. Right. So yeah. So here x mu is basically some arbitrary point in Minkowski space. Q mu is this, as we just said. This delta was some regulator which you have to use in order to make sense of this integral. But the essential property of this so-called conformal primary wave function, which I want to point out, is that basically that these objects they are solutions to the massless Klein-Gordon equation, and that is kind of obvious because the plane waves are the solutions of massless Klein-Gordon equation. And these phi's and what you can show is that these phi's basically transform in the same way under SL2C as our single particle state, meaning that they also transform as actually primaries under the action of SL2C. Okay. So in this case, I actually, so I just showed you what this conformal primary wave functions look like for this case of scalars, but you can work out more complicated examples. Let's say like the case of particles with non-zero spin, and that has also been actually worked out. So if you see, so if you see papers by Pastarsky and by Shu and Shao, then they also work out examples of this conformal primary wave functions when you have non-zero spin. Okay, so then, okay, so with all those definitions at hand, we finally can write down the celestial amplitude, and the celestial amplitude is where, so then the celestial amplitude is basically just a Mellin transform of the standard S matrix, and that is because the standard S matrix is just some overlap of the creation and annihilation operators. Okay, so you have some set of creation operators which correspond to, let's say, the asymptotic in state, and you have some set of annihilation operators corresponding to the asymptotic out state, and basically their overlap is what we call the S matrix. And we know, and as we just defined, and that since we just defined sort of this, and since we just defined this set of conformal primary operators, which were Mellin transforms of this creation annihilation operators, then using that definition, what you basically have is basically the following. So then the point to take away from here is that if you perform a Mellin transform of the standard S matrix, then that can be interpreted as behaving like an endpoint correlation function in some conformal field theory. And this conformal field theory is sort of nowadays referred to as the celestial conformal field theory for obvious reasons. Okay.
So one question.
Yes.
So if I were to expand the field in terms of these creation annihilation operators, then the corresponding modes would be the guys you just showed, the
exactly
primary wave functions.
Exactly. Yeah.
Okay.
Right. Yeah. Right. Okay. Good. So this we have already discussed now. So now it is it immediately follows from the transformation property of the individual operators that this whole object is basically this object which we are interpreting as a correlation function, so that in a 2D CFT indeed transforms as a 2D CFT correlator under the action of the Lorentz group, or equivalently SL2C. So that so that basically works now. So that basically works just by construction. Right.
Just one small.
Go
the amplitude that you had written, that has the delta function, momentum conserving delta function, or
So in this case, so this amplitude has by definition the momentum conserving delta function, because the way I'm defining it, so this is basically the entire S matrix, because this is abstractly being defined as the overlap between ingoing and outgoing states.
Okay. I see. Okay.
Okay, great. Okay, great. Okay, so now let me actually discuss some points about space-time translations. So what we have been doing so far is that we have defined this new basis of states, which makes the underlying conformal symmetry completely manifest. But we can also also ask that what happens to actually space-time translations, right? Because as we know that the standard S matrix is basically not just Lorentz invariant. We know that the S matrix. So we know that the S matrix also has to be Poincare invariant. Okay. But what happens is that in this definition of this single particle states, which is given by Pastersky, Schaub, and Strominger, in this case, the action of space-time translations on the S matrix, on the Mellin transformed S matrix, or the celestial amplitude, as we are calling it, so that is a bit obscure. And that can be, and an example of this is the following. So say suppose you perform a global time translation, okay? Then you know that if you have some creation and annihilation operator, then under a global time translation, which is implemented by the Hamiltonian, so in that case, you basically know that your creation and annihilation operators basically get multiplied by a factor of the energy, right? So then if you right. So now if you ask what happens to this thing when you do a Mellin transformation, then what you basically have is the following. So you basically get an extra factor of omega here, and the effect of that extra factor of omega is basically to shift in this case the conformal dimensions of these operators by factors of half, right? Because what is happening is that because of this extra factor of omega, what is happening is that basically the scaling dimension delta is getting shifted by a factor of 1, or equivalently the left and right conformal weights are getting shifted by factors of half. Okay. So then the point is, and that if you do a space-time translation, then what happens is that basically the labels which are this left and right conformal weights, which we are using to actually sort of label our external particles. So these labels in this case get changed when you do a space-time translation. And so therefore, if you start with let's say suppose one particular correlator which has, let's say, some assignment of, let's say, scaling dimensions, and you act with a space-time translation generator, then you basically get back a new correlation function, right? So in that sense, the geometric action of space-time translations is not manifest in this definition. But what I'm now going to describe is that there is a certain modification of the Mellin transform that we have discussed so far, which, for lack of a better name, is just called the modified Mellin transform. And with that definition, we will see that one can also make the action of space-time translations geometrically manifest, and that will also have some more sort of advantages, as we will see.
So Sudip, here you considered infinitesimal time translation, is it?
So in this case, I am considering infinitesimal time translations.
Yeah. Okay.
Good. So now, so now let us come to what is known as the modified Mellin transform, and this is something which was worked out by Shamik. So in this case, basically what you do is that you start with your standard Mellin transformed single particle states, and you basically act on them by and you basically act on them, and you basically act on the states by this operator e to the power minus IHU, where H is basically the Hamiltonian of your system. Okay. So that if you write this action down explicitly, then what you have is that you again have the origin. Then you again have So in this case, you again sort of have the Mellin transform, which we had before, but the only change now is that you have these extra exponential factors. Okay, so in this case, these extra exponential factors, they and actually come along for the ride as well. So now you may ask that what is basically this interpretation of this extra label u. Okay, so now we will see in a short while that this extra label u has the interpretation of a time coordinate, and it can be thought of as either the retarded or advanced time coordinate along null infinity. Okay, and we will see in a brief while that why that interpretation makes sense. Okay. So in this case, just
naive
for
question, I have a naive question. So why is it obvious that the e to the minus ih u commutes with the Mellin transformation, that you can bring it inside and
with the Mellin transformation? So in this case, there is nothing subtle about commutation, because in this case, what I'm so basically in this case, what I'm just using is basically I'm using the original definition of this Mellin transform states. I'm just writing it as some integral over energies of single particle states, right? So now the Hamiltonian just hits those single particle states, and those were energy momentum eigenstates, and so therefore you just basically get this e to the power minus I omega u factors.
I see. Okay, so doing the Mellin transform before or after taking this action, there's no.
Great. So as I said, that for now, actually, believe me that this so for now, believe me that this extra label u plays the role of a time coordinate along null infinity, and I will justify that in a second. But just to point out a couple of features. So basically in this case as well, if you try to compute, let's say if you try to compute, let's say the inner product of this modified Mellin transform states, then once again you will find that they are also delta function normalizable only when the scaling dimensions again lie on the principal continuous series, which means that these deltas have to take the following form: 1 plus I lambda, okay, where with lambda being some real number. And as we did before, we can also talk in terms of creation annihilation operators. And in this case, the creation annihilation operators in this modified Mellin basis are defined in a similar fashion. In terms of defined in a similar fashion in terms of the Fock space creation annihilation operators, and the only new thing that we have is basically this exponential factors. Okay. So now what you can check. Okay. So then the next thing to obviously ask along the lines of what we have been doing so far is that how does the Lorentz group act on these objects? And you can work that out. So I will not actually bore you with the details of the derivation in this case, but let me just tell you the answer. So basically, if you try to see how this transforms under SL2C, then you will find the following answer. So this change in ZZ bar, which is given by these two factors. So that is familiar from before, because that is just the standard sort of action of the SL2C group on ZZ bars. But now you have this U, parameter as well, and what you can show is that is that basically the change in U in this case takes the following form. So U basically changes as U by AZ plus B mod squared plus CZ plus D mod squared. Okay. And so this is also very easy to check. It's just actually 2 lines of algebra, and you can convince yourself of this. Okay. So now, okay. So the next thing that we can check is that how these operators change under the action of space-time translations. So let's suppose we take some arbitrary 4-vector in Minkowski space, which is denoted by L mu. And we take the space-time translation generator, which is, let's say, capital mu, and then we just act with this on these operators in the standard form, in the standard fashion, and then what you will find is that basically the operator shifts, or basically the arguments of the operator change in the following fashion. So basically what you will see, so in this case you will basically see that basically the scaling dimensions, they remain the same. So h and h bar remain the same as that of the operator before doing the translation. But what changes is that this u coordinate actually gets shifted. So basically this label u gets shifted by a particular function of this, which depends on this zz bars, and also on the components of this 4 vector L mu. Okay. And this f of zz bar has f of zz bar has so that has some explicit form, and that is given by something which looks like this. Okay. So basically the takeaway point from this is that if you do a space-time translation on this modified Mellin basis states, then in that case what you find is that the zz bar coordinates don't change. The scaling dimensions also remain the same, but this extra label u, so that gets actually translated by a function which depends on these zz bars. Okay. So then, so with that definition, we can write down what is known as the modified Mellin amplitude, which is just the standard, which just again involves the standard Mellin transform of the Fock space S matrix, but the new addition here, compared to our earlier definition, is that we have these exponential factors, exponential factors for the right. Okay. And so this object can once again be interpreted as basically as being some correlation function of some set of operators. Okay, and this again, for a lack of a better name, is basically called the modified Mellin amplitude. Okay. Right. So then the next. So then this is okay. So now these things are obvious. What you can check is that how what you can check is how this putative correlation function transforms under the action of the conformal group, and that transforms in some very explicit way as shown here. And the main feature here is that if you now do a space-time translation, where the u coordinate basically shifts in this particular fashion, then it turns out that this modified Mellin amplitudes are actually invariant when you do a global space-time translation. And so that is one of the main features of this, modified Mellin amplitude, that you see that the amplitude is invariant, and also the geometric action of space-time translations is completely manifest, which was not the case in our earlier definition.
Excuse me.
Yeah. Yes. Go ahead.
The line up above where you wrote how the just up above, which you can see half. Yes. In the standard study of 2D CFTs, are there objects that are known to have this kind of a rule?
Yeah. So I will come to that. So basically I will come to that now. So basically this object which I have written down. So basically this correlation function which I have written down, that is not a correlation function in a two-dimensional conformal field theory.
Right.
So in this case I will basically give a sort of interpretation to this in a second. So in this case, just hold on for a few seconds.
Thank you.
Okay, good. Okay, good. So basically, as of now, just take this as basically the definition of this modified Mellin amplitude. That it is basically some so that is basically some actually yes. So this is some actually integral transform of the standard S matrix, and the point of defining this new integral transform was to make the action of space-time translations actually geometrically manifest.
Okay, thanks.
Okay, so now let me clarify some of the things which you have raised. So for that, let me make a few comments. Okay, so the first comment is the following. Right. So from these two properties of how this operator is transformed, or rather, and actually this set of properties. So for example, this guy, the transformation under SL to C, and the transformation under the space-time translations, we see that we basically see that these transformations induce the following geometric transformations on these UZZ bar labels. Okay, so for example, if we do a Lorentz transformation, then these UZZ bars, they change in the following fashion. Okay. On the other hand, if you do a global space-time translation, then it changes. Then then in that case, the U coordinate shifts. It gets translated by a function of Z and Z bar, but the ZZ bar variables, they themselves don't change. Okay. So so now the point which I want to make is the following. Yeah. Yes. Go ahead.
Is this FZZ bar L the same as the Q mu times L mu? Because it
yes.
occurs to me that you could just rewrite this as L times Q, right? This is
L? Yes. So so that is right. So that I swept under the rug, but as you correctly observed, is that this f of ZZ bar was just that was basically L dot Q. Exactly.
Okay, thank you.
Great. Actually, very good. Yeah. So the point now which I want to make is the following: is that basically from this geometric transformations of the UZZ bar labels under the action of the Lorentz group. So basically, if you stare at these transformations for a while, then what you immediately can realize is that basically this set of transformations of the UZZ bar labels is precisely the same as the action of the Poincare group at null infinity when you write the metric of Minkowski spacetime in the so-called Bondi coordinates. Okay. So basically, these Bondi coordinates are a set of coordinates which in which you can write down the metric of Minkowski space, and that basically takes the following form. And in this way of writing the Minkowski metric, so basically in that way of writing the Minkowski metric, U is basically the retarded time coordinate, so it depends on where you define it. But this U coordinate is basically the time coordinate. So it is the time coordinate which runs on sky plus minus, and ZZ bar are basically the stereographic coordinates on the celestial sphere. So therefore, so basically the point is that if you take this metric and ask how does the Poincare group act on these coordinates, then you will precisely find actually this set of transformations. Okay. So then from that point of view, what we can think of is that this UZZ bar labels which appear in our Mellin transforms can be naturally thought of as coordinates on null infinity. Okay. And so since we have that, we can give a natural interpretation to this modified Mellin amplitude, and we can say the following: that the modified Mellin amplitude can be regarded as a correlation function in some putative 2 plus 1 dimensional quantum field theory, which lives on null infinity, and which you can think of as giving a holographic description of the quantum of in this case the 3 plus 1 dimensional theory of quantum gravity in the bulk. Right. So in this case, the difference from the standard Mellin transform is the following: that in the standard Mellin transform, we interpreted that object as being a correlation function in two-dimensional conformal field theory on the celestial sphere. But the way we defined this modified Mellin amplitudes, it's more natural to think of them as correlation functions in a 2+1 dimensional theory, which is defined on which would be the dual description of sort of quantum gravity in 3+1 dimensional in the 3+1 dimensional Ball spacetime.
A quick question: in the paper by Pastor and Shaw, they first took the hyperbola, the Euclidean ADS hyperbola. They took the massless limit to derive this Mellin transform.
That's right.
Is there a way where, I mean, so I didn't understand it completely, but I thought that was a unique limit. Is there some generalization of this modified Mellin amplitude for massive particles as well?
Oh yeah. So so actually that is a very good question. So basically, as of now, it is not known. It is not known how this modified Mellin amplitude sort of so how this definition extends to massive particles.
Okay.
Because and the main reason for this is the following. So basically, you see that this representation of in terms of some object which lives on null infinity is very natural for the case of massless particles, right? Because massless particles reach out to null infinity, but massive particles don't. So therefore, it is so therefore massive particles don't naturally sort of live on null infinity, and so therefore this modified Mellin amplitude definition doesn't quite go through for massive particles.
Massive. I see. And one more additional question.
Sure,
so in the case of the usual Mellin amplitudes, there is a way to derive this soft factorization where you take this conformal dimension going to certain values. So
exactly.
Is that story the same here?
Yeah. So that story in this case is basically the same. So in this case, we will actually go through that story in actually the next lecture. Yeah.
Okay.
Yeah.
Thanks.
Yeah. Okay, good. Okay, great. Yeah, so so that was that. Right. So what's next? Right. Yeah. So the last thing here which I wanted to point out was about this 2-point function in this modified Mellin basis. So so in this case, you can actually go ahead and compute what the inner product between states in this modified Mellin definition is, or equivalently the 2-point function. And what you can show is that the 2-point function basically in this case takes a form which is like this. Okay, so in this case you still have this delta function, which in this case is basically this delta of z1 minus z2, which basically enforces the condition of momentum, which basically arises out of momentum conservation, and tells you that a free massless particle enters and exits the same point on the celestial sphere. Okay, but the difference now is that because of these u coordinates, you basically have this extra dependence on these u levels, and that takes the following form. Okay, so now I want to point out a nice feature of this 2-point function, which is the following: is that suppose you take this you take this object and you basically translate the u1 okay, so you basically translate these coordinates ui's by an arbitrary function of the zz bars. Okay, then because of this delta function, so then it is obvious that because of this delta function, even if you shift the u coordinates by an arbitrary function of zz bars, then the 2-point function will remain unchanged. Okay, so this is in a sense actually a manifestation of actually BMS super translations, because in BMS also so basically the way BMS acts is that it basically shifts the retarded time coordinates at null infinity by an arbitrary function of the angles of the angular coordinates on the celestial sphere. Okay, and so in this very simple example, we see sort of incarnation of that this 2-point function is basically invariant under this BMS super translations. But it turns out that this exact invariance of the 2-point function is actually accidental, and this and we know from this, and if you have followed this, and if you have been following the recent study on asymptotic symmetries and so on, then you know that these asymptotic symmetries get actually spontaneously broken by a particular choice of the Minkowski vacuum. And so therefore, if you try to compute higher point functions, then you will see that higher point functions are no longer trivially invariant. Or if you try to compute higher point functions in the interacting theory, then higher point functions will no longer be actually sort of trivially invariant under this transformation. And so that will be a signal of the fact that the BMS symmetry gets actually spontaneously broken, and we will get some word identities corresponding to that. And we will see the consequences of those word identities. So so basically we will see what those consequences are in the next lecture. But for now, I just wanted to point out that the 2-point function has its accidental symmetry. Okay. Okay. So the last comment which I want. Okay. So I want to make a couple of more comments. Okay. So
I
go ahead.
Something. So it seems that there is no straightforward way to go from this 2 + 1D kind of a thing you have back to the 2D safety amplitudes, right? Because I don't see how from this 2-point function you could straightforwardly get back the 2-point function of the 2D CFT that you first showed us.
So what you have, so actually, so this is slightly, it is a slightly tricky thing to do, but what you can do is that you can try to set all the U coordinates to 0, but then you have to,
that wouldn't work, right? I mean, you would have to set them in some specific way because the thing that you put it in that square, the red square, that seems to misbehave. So how would one do that? I wanted to know.
Yes. So basically in this case, what you see is that because of this 1 by U1 minus U2 factor, this actually has a divergence, and okay. So first of all, if you keep the U's fine, if you have this form, then of course this does not exactly make sense. It has to be made sense with an I epsilon prescription. But the thing is, that if you, what you can show is that if you carefully take this limit where let's suppose U1 tends to U2, then in that limit, after you properly regulate things with the I epsilon prescription and all, so what you can show is that with an I epsilon prescription, if you take U1 to U2, then you basically recover the 2-point function. So then you basically recover that delta function answer, which we had in the previous case.
Okay, thank you.
So in this case, basically the only thing, so basically in this case, the only thing which you have to show is that in the U1 going to U2 limit, this object becomes this object becomes this guy. It becomes delta of λ1 plus λ2.
Right.
Because this is the object that we had lost.
Okay,
so so this thing is a bit short, is a bit non-trivial to show, but it can be done.
But it kind of follows, right, from the definitions with the E, because you inserted this extra E factor in the definition. You take it.
Exactly. So that should follow. Yes, I agree.
Yeah, that's true. But just seeing this 2-point function, it didn't seem how I could get back that one. But okay.
So from this form of the 2-point function, it is not very obvious because its limit is a bit subtle. But that can be taken care of.
Okay.
Okay. Good. So the last couple of points that I want to make are the following. Okay, so as of yet, what we have been doing, okay, so one motivation which I gave you for looking at this modified Mellin transform was to make the action of space-time translations geometrically manifest. But there is, okay, but you might say that, okay, okay, so I'm not very interested in making that transformation geometrically manifest, because even in the ordinary Mellin basis, although it is not geometrically manifest, I know how it works. Okay. But there is a more practical sort of need for this modified Mellin transform, which is the following: is that basically this Mellin transform defined by Pasterski, Shao, and Strominger. That object when you actually try to compute in practice, so that object in most cases is actually quite badly behaved. In particular, if you want to compute, let's say, the Mellin transform of, say, suppose actually graviton scattering amplitudes, then it turns out that this Mellin integral is actually UV divergent. Okay, and that happens because of actually the fast growth of so that happens because of the fast growth of actually graviton scattering amplitudes in any effective field theory. But it turns out that if you use this modified Mellin transform prescription, then in that case, this e to the power minus I omega u factors, which one inserts, then this fact, then upon proper analytic continuation of this use, what you can show is that these exponential factors provide some damping factors to actually the Mellin integral, and that sort of regulates this UV divergence, which you ordinarily encounter. So from a practical point of view, if you want to actually do calculations, in particular in the case of gravity, then it is actually so in that case, it is actually more convenient to work with the modified Mellin transform than to work with the ordinary Mellin transform. So just to make one more comment along these lines, so basically in this case, if you hear talks on this subject by Strominger and others, and in this case, basically particularly Strominger, then you might come across these statements that the modified Mellin transform in Einstein gravity is completely divergent, and so that is a very bad thing. And that is usually seen as a bad thing, and in that case, what Strominger likes to advocate is that basically you should define the Mellin transform first by going to string theory, and then you should try to take the low energy limit, and then define the Einstein gravity Mellin transform of Einstein gravity amplitude by taking the low energy limit of string theory. So that is completely valid. So that is a completely valid sort of thing to do. But in my opinion, a more practical way of doing things for calculations is to just actually sort of use this modified Mellin transform definition. But anyway, okay. And another feature that I wanted to point out is that basically what you can show is that the constraint of global space-time translation implies that if you have any 4-point celestial amplitude, be it the ordinary Mellin transformed amplitude or even the modified Mellin transform amplitude, what you can show is that basically any 4-point Mellin amplitude will be proportional to a delta function of z minus z bar, where this z and z bars are basically the following, certain ratios of this zi's and z bar i's, and these go by the name of cross ratios. So what this statement basically says is that basically in any 4-point function, what you have is that basically the cross ratios have to be real. Okay, and this is basically forced onto you by 4-particle kinematics. And here also you see that this is another place where you see a departure from standard sort of two-dimensional CFTs, because this sort of a delta function which enforces the reality of the cross ratios, so that we don't encounter in the standard discussion of 2D CFTs, right? In the standard discussion of 2D CFTs, 4-point functions don't have such actual delta functions of this form. But in this case, because of actually 4-particle kinematics, you do sort of end up with funny factors like this, and that's sort of a departure from from the standard 2D CFT story. Okay. So with that, I'm sort of done with this more or less the basics of what I wanted to say about Mellin transforms for massless particles. So now, okay, so guys, yeah, so actually Madhu, how much
You have 10
longer can I
minutes
go on
because
for?
we started 10 minutes late. So you can take 10,
Okay.
15 more
Okay,
minutes.
great.
Okay.
Okay, great. Okay, great. So, okay, so maybe in 10 minutes, let me tell you some, a little bit about this, a little bit of the story for massive particles, and then we can end for today. Okay. Okay, so let's see what happens for massive particles. Okay, so let's start simple. So say suppose we start with a massive particle and which with let's say some mass m. Then we know that basically the on-shell condition is basically this guy, m p square equals minus m square. When we yeah, and if you write it out in terms of components, then we get some equation of this form. And this equation, if you stare at it, then you automatically recognize that this describes the embedding of a three-dimensional hyperbolic space, or equivalently Euclidean ADS3. Yeah, so this basically describes the embedding of three-dimensional Euclidean of three-dimensional Euclidean ADS3 inside of and actually yeah, so that inside of 3 plus one-dimensional Minkowski space. Okay. So now, in what I'm going to do, right? Okay. Okay. So now I'm going to choose. Okay. So now I'm going to write down these momentas for massive particles using a particular parametrization, which will be sort of similar to the parametrization for massless particles that we used before. Okay, and that will be convenient for what I'm going to say. So basically for that, let me choose okay, so basically, as we said, that this massless, okay, sorry. So in this case, these massive particles, they naturally define an embedding of Euclidean ADS3 inside 3 plus one-dimensional Minkowski space. So in this Euclidean ADS3, let's choose what are called Poincare coordinates. And in Poincare coordinates, I am sure those of you who are familiar with ADS-CFT have seen this metric 1,000 times, which is basically this metric. Okay, great. So then what you can so then what you can show is that basically this massive part is basically this massive momenta that can be parameterized in the following fashion. Okay. This is something very simple which you can convince yourself. So with that definition, or with that parameterization of the massive momenta, what I want to tell you about is that how you can go about defining the celestial amplitude for massive particles. Okay. Right. So, but for that, I'm not going to repeat all this discussion of single particle states and how they transform and so on. So all of that can be done here as well. It's just a little bit more complicated. But let me just tell you how to simply arrive at the final result. And this is also how actually Pastarsky and Shaw discussed it in their original papers. So, okay, so in this case, let us also consider, in this case, these conformal primary wave functions, which would be the counterpart of our familiar plane waves. So basically what we seek is that we seek objects of this form, some wave function, which is characterized by some scaling dimension delta. Okay, and it is a function of some bulk coordinate x mu and some coordinates z bar on the celestial sphere. Okay, so then so from so now what we want is that basically we want this object to solve to actually solve the massive Klein Gordon equation, which is this object. Okay, and we also want this object to sort of transform covariantly under the action of SL2C, right? So in this case, I'm considering a simple case. I'm considering this to be a scalar wave function. So then in this case, under SL2C, I want it to transform in the following fashion. Okay, great. Okay. So now, since this conformal primary wave function, the thing which we want to find out is so that since that basically solves the Klein-Gordon equation, you should be able to expand it on plane waves, because plane waves are a solution of the Klein-Gordon equation, right? So you should be able to write it as some superposition of plane waves. And all you have to find out is that basically you have to find out the Fourier coefficients in that expansion. Okay. And then the property of and then there is and then we can use this property that this object has to transform covariantly under SL2C. So therefore, what should happen is that basically these Fourier coefficients should also transform covariantly under the action of SL2C. And that demand basically uniquely fixes what those Fourier coefficients can be. And these Fourier coefficients are basically given by actually the so-called bulk to boundary propagators. Okay. And so therefore, at the end of the day, what you can do is that you can write down the scalar conformal primary wave function as basically a Fourier expansion in terms of plane waves, with some bulk to boundary propagators acting as the Fourier coefficients. Okay, so there is a way of and again, those of you who are familiar with ADS-CFT know that the bulk to boundary propagator for let's say a scalar particle in ADS that takes the following form in ADS3. Okay, so this I can skip. Yeah, so then by construction it will transform as a primary under the action of SL2C. And yeah, and in this case also what you can show is that the massive scalar conformal primaries, they also are delta function normalizable only when the dimensions, the scaling dimensions delta lie on the principal series. Okay. And then and then the last thing which I wanted to show is that you can compute the inner product between these guys, and in this case what you find is that you don't find in this case you find a more or less standard sort of 2D CFT form. You don't see these funny delta functions, and that is natural here, because since massless particles don't make out to null infinity, so then massless particles so in this case, since massive particles don't make out to null infinity, they are sort of smeared over null infinity, and so therefore if a massive particle comes in, then it does not have to enter and exit at the same point on the celestial sphere. And so therefore you sort of get the standard 2D CFT 2-point function form. And and now if you write down your momentum space S matrix, not in terms of plane waves, but in terms of these conformal primary wave functions, then from that you can define your massive celestial amplitudes as well. And that in this case takes a more complicated form. It is still given by an integral transform of the Fock space S matrix, but this integral transform now has these factors of actually the bulk to boundary propagators, which you get for all the external lengths. Okay. So I think I will actually stop here for the moment. So next time, so just to sort of give you a teaser of what is to come next. So next time we will basically consider so next time we will consider actually the analog of soft theorems, as actually one of you pointed out during the talk, that there is a way of actually there is an analog of the energetic soft theorems in this Mellin space as well, where the scaling dimensions of the external operators, they tend to certain integer values. And we will see that those soft theorems take the form of certain word identities, and we will study and we'll try to see what are some of the consequences of those word identities. Okay, guys. So with that, I will end for today.
That is all. Thanks, Sudip, for the excellent talk.
Can I ask just a reference question? Is there a place about the? I mean, is there a nice reference for principal series representations or general?
Right. Reference for principal series. Yeah. So actually, yeah. Let me think. Yeah. So some of this CFT literature discusses it. For example, if you open papers, let's say by Simon Staffins and all.
Right.
Yeah. So I mean, this principal series usually comes out when you try to do this conformal block decomposition. Not conformal blocks, but you try to write down these conformal partial waves. Then the point is that these conformal partial waves satisfy nice orthogonality properties and so on. When you take the dimensions to belong to this principal series, and so that that is a useful thing in 2D CFT. Yeah.
I see. So papers by Simon Staffin should.
Papers by Simon Staffin should have it.
I wanted to ask something. Maybe you explain this. At some stage, will we see symmetries or not?
Right. So good point. So this we will actually discuss sort of in the last lecture. But just to answer your question. So basically in this 2D CFT which we are trying to get at, which is in a sense defined by taking the Mellin transform of our S matrix elements for massless particles. So that 2D CFT, since it has the global conformal group, now that immediately sort of gives you a hint that once you have the global conformal group, then I should have the full Virasoro. And there is indeed a construction by Strominger and collaborators, where they showed that you can, using the subleading soft graviton theorem, you can construct an operator whose insertion inside the S matrix, or equivalently whose insertion in the celestial amplitude, gives you something which looks like the word identity for the which looks like the stress tensor word identity in a 2D CFT. Right. And that tells you that there should be an underlying Virasoro symmetry. Yeah.
Right. So, well, that then leads me to ask more stuff. Like the thing is, what would the small c be? What would the central charge?
Good. So basically, as of yet, what has been done so far in that it seems that the central charge is 0. But that conclusion is born out of calculations which have been done only for tree level amplitudes.
Right.
But as of now, it seems that the central charge is 0. Okay, but I should mention that if you read this asymptotic symmetry literature, then if you read, for example, discussions of, let's say, this BMS group and so on, then in that discussion there is a discussion of actually central charges which appear in the so-called extended BMS algebra, which includes super translations and also super rotations, which is another name for Virasoro. And so basically there is some central charge which appears in that algebra, but that central charge is not is actually not just a number. So that central charge actually depends on the fields in the theory. So that is not a conventional central charge actually. But actually this is an open question, that what the central charge in general is actually.
Right.
So that we don't know as of yet.
So then you would say that we also don't know how to then decompose what the 4-point function would be in terms of 3-point functions, right? Because unless we know what C is, we cannot really actually write down this expansion of 4-point function in terms, like factorize them in terms of 3-point functions. Right?
No, so that so there the point is the following. So in this case, you could ask that is that given a 4-point function, can I decompose it in terms of Virasoro blocks or not?
Right.
So basically That nobody has shown. So actually, there is I think there is a paper that is about to come by Strominger and collaborators, who show that there is a conformal block decomposition that you can do, but that conformal block decomposition is not in terms of Virasoro's. So it turns out so actually the point is that it is not clear how this Virasoro appears at the level of the OPE actually. So this is something which we will discuss actually the next time also. So in this case the point is that we have not just Virasoro, but there are actually other symmetries in this case as well. So for example, there are super translations and so on and so forth. Okay. So then whatever block decomposition one uses, then that block decomposition also should involve these other symmetries.
Right. So you're saying that it is some kind of extended Virasoro, some extension of it.
No. So yes. So basically, So in this case, you could So in this case, you could call it that. But what I would call it is that this would be some analog of BMS blocks. So you would have some notion of BMS conformal blocks, which should incorporate super translations as well as Virasoro. So in this, that would be some general object which has not been constructed so far, but that would be the most appropriate object to expand these 4-point functions in.
Right. Okay, thank you so much.
Sure.
Any other questions? Okay, if there are no other questions, let's thank Sudip once again, and we'll all meet again next week.
Okay, so thanks guys, and take care. Bye. So see you next week.
See you next week.
See you.
Oh wait, there's a question by Anish in chat. He's saying, post notes.
Oh yes. So I will actually send you guys the notes. Yeah. Sure.
Okay, great. Okay, see you next week.
Okay, see you. Bye.